We have the integers from 1 to 25. We're going to remove some, split them into two groups so the products are equal. We want to remove the smallest amounts. Okay, well, first up, let's get the numbers from 1 to 25 written down. Now, immediately, some are problematic because 23 is a prime number. And so if it's on the right, in the right-hand group, there's no way in the left-hand group you're going to get a multiple of 23 because by definition, 23 is only divisible by 1 in itself. So we're going to have to get rid of 23. And for similar reasons, we're going to have to get rid of 19, 17, and even 13. With 11, even though it's prime, we've got a multiple of 11, another multiple of 11 in the group. So as long as 11's on one side and 22 is on the other side, that will be okay. You'll get a multiple of 11 either side. It's just whether we can balance it out to make it so the product's equal on the two sides at this point. So I think what we have to do really, although I suppose we could, okay, it's not a bad idea to just add up what we've got so far. So I've got 30 plus 19 plus 23 plus 42. So I'm up to 72, the sum of the ones that we've taken out. Okay, so this actually shows us that we're going to need to take out some more. I'm going to write the rest as a product of their prime factors. Okay, some of them are sort of already all right, but here we've got 2 squared, 2 times 3, and so on. Okay, and what we have to have is an even number of each power for this to work. If you have 2 to the power 4 on the left-hand side, you're going to need to have 2 to the power 4 on the right-hand side for it to balance out and be equal, now that we've got the prime factorization. So let's add the powers of 2 to start with. See, check that that's even. So we've got, oh, don't forget about this one. So we've got 1, 2, 3, 4, 7, 8, 9, 10, 11, 15, 16, 17, 18, 19, 22. So overall, we've got 2 to the power of 22. So if we can split it, so we've got 2 to the 11 on the left-hand side and 2 to the 11 on the right-hand side, then we're all set. We won't need to get rid of any more powers of 2. Gonna have to do similar now with 3. And remember, the 1 can go anywhere. That's not a problem. We don't need to get rid of that. So 1, 2, 3, 4. Oh, sorry, I missed one here. 5, 6, 7, 8, 9, 10. 3 to the 10. So again, this is not problematic as long as we can split them the right way. Okay, let's look at the 5s. So these are quite quick to find. Just powers with 5, 10. So 2, 3, 4, 5, 6. 5 to the 6. And finally, 7. Got 1, 2, and then, oh, sorry, not finally 7. 7 cubed, but that is a problem. And then 11 is actually the last one. We've got our 11 squared. So all the powers are even except the 7. So we know for sure that it's not going to work as it stands. If I get rid of the 7, then it will actually become 7 squared and it might work. And that would take us up to 79 as our sum. So it's very tempting to go with this now. Gotta be honest, when I did this question, I said we can probably arrange the rest. We're under time conditions in theory in this challenge. So in a full problem, when you have enough time, Olympiad and so on, you should show that it does work, even though in theory it might work. Just need to check that it does work. But in this sort of situation, I don't know, because sometimes you rush it and think it might be okay and make mistakes. But if you want to show it comprehensively, you do need to now check that you can construct um, a number that's going to be 2 to the 11 times 3 to the 5 times 5 cubed times 7 times 11. I don't think it'll take too much time, just like sort of circle some of them. I'm not going to do it here. I'm going to take one that's already been done in the answers. It is possible. It feels like it'd be highly unlikely to not be possible in this case, to be honest, just because, there's so many different sort of combinations you can make and nice numbers like 2 and 3 that you can swap around if you need to. Some of them, a bit more involved, like you have to have 2 cubed and 3 together. But as long as you sort of separate 22 and 11 and 7 and 14, then you can make it work in more than one way, I think, but this is one possible answer. So yeah, the ones we have to get rid of are the ones I've crossed out. They sum to 79. That's it.